Hello, everyone. Thank you for coming to this DESIR Winter School. Today, I'm going to talk about open research notebooks. First, I'm going to introduce myself a little bit. My name is Javier de la Rosa. I'm a postdoctoral fellow working with natural language processing at UNED in a ERC, European Research Council project called Postdata, which deals with ways of standardization for poetry. Part of my duties there are developing natural language processing tools so we can analyze poetry automatically and then feed it into a network of ontology so we can share it freely with the research community. I have a mixed background. I have a master in artificial intelligence, but also a PhD in Hispanic literature. I used to work at Stanford for a while. Before that, I used to live in Canada, working also there. Until now, we have seen what is data in the humanities, how we define it, what are the different kinds of data that we can find. We have also seen ways of citing data and citing software, what is a permanent identifier like DOI. And today we're going to talk about open research notebooks, okay? First of all, I want to show a bit of a mental map, a mind map, so you can place exactly where the open research notebooks are in the entire ecosystem of open science. So far, we are about here. It's hard to read, so this is the entire framework of open science, which is divided in open access, open data, open science policies, and then there is a section for open reproducible research. And that's the key word in the reproducible. Part of that is the definition. What is that we understand by reproducible? What are the open lab notebooks, which is kind of the same thing? How can you guarantee that something is reproducible? And what are the tools and the means that make that a reality? I try for every slide in here to provide source, should be MLA kind of. So you can go there to the original source, and then if you have any sort of interest in that particular topic, you can read more about it. Notebooks are virtual environments. That's it. It's the equivalent of a field diary. When you go out in a field trip to take notes of your research, now we do that digitally in a virtual environment. It basically tries to implement the idea of literate programming, which was introduced by Donald Knuth, the famous computer scientist at Stanford in 1983. And he defined that literate programming basically have two components. One is weaving, which is basically being able to generate a comprehensive documentation of the program and how can you maintain the program, how can you keep it up to date. And also tangling, which is not only documentation for the program, but also the actual machine executable code, both living in the same kind of environment. That was the idea that Donald Knuth had back then. He actually tried to implement it at least twice. He created a thing called web before the web actually existed. He thought that it was a word that no one ever used for computer things. So he called it web and tried to create this literate programming environment in a pseudo language of C language. So you can have all the code, all the machine readable code in one file, and then all the documentation, and then put it all together in this C-WID format. The idea that he devised is that every piece of literate programming is in itself a piece of art. Maybe too optimistic, but in the end, he succeeded, not by its own efforts, but the force of the community around it. So the main goal is to be able to document research procedures, data, and calculations. Findings is the part that research notebooks added recently that were not included in the original ideation of the literate programming. So when you have an environment like this, you can also track your methodology, and you make easier to reproduce your results because you have all the code that leads to the results, but also explanations on how to do it, what decisions you made, and why you made them. After 1983, In 1988, by the end of the decade, Stephen Wolfram, which was a mathematician based in Seattle, I think, he created this framework called Wolfram Mathematica 1.0. Maybe some of you have worked with Mathematica before, but it's nothing new. So it's been around for almost 30 years now. And right since the beginning, Stephen Wolfram had the idea that you could have in the same environment the computation and the output of the computation. In iterations after the 1.0, he introduced symbolic calculus, numerical calculus, integrations, and all sorts of stuff until the Wolfram Mathematica that we know today. A few years later, a group at the University of Waterloo in Ontario, Canada, created the Maple. Maple was kind of a re-implementation of Wolfram Mathematica, but in its own terms. It was by a group in the university who wanted to try do an implementation of literal programming. Then it became its own company, and then there is also Maple. Even in nowadays, there is a new version of Maple actually coming as of last year, I think. Again, the same thing. Symbolic calculations, you have the source code using whatever language they decided to use, and then the output of that computation. Everything in kind of the same environment. In 1997, a few years forward, MUPAD, which was acquired by MATLAB, also created something very, very similar to the notebooks that we saw before. At that point, already, the conception of a page in which you wrote your equations, you wrote your calculations, and then you saw inline the results and the outputs was already established. So they created this thing called the MUPAD. They became a company, and then the company was acquired by MATLAB, and MATLAB used that notebook for the in-house notebook production. Fast forward to 2001, Ipython came into the game. Ipython was an extension of a terminal and a console, but in that terminal, they added what is called a REPL. It's basically a read, eval, print, loop. So you read the commands, you evaluate the commands, you print the results, and then you wait for the next command. So they added that on top of the basic terminal of Python. They call it Ipython. Fernando Perez, actually, a University of Berkeley scientist, I think, and they released it in 2001. But it wasn't until 10 years later that Ipython hope it doesn't fall off again. It's all good?
Yes.
So at the beginning of the decade in 2010, 2011, Ipython released what we know now as the notebook, which was basically a front end, a web front end to the Ipython. So they created a way to interact with an Ipython kernel. So you can write your Python code and then send it to something called a kernel. So the kernel evaluates the code, and then the results come back to me. But instead of using a terminal, they use a web interface. This was the realization that the model was actually very easy to extend. So why stop there? They did not. In 2014, they split the project from Python, and then they created the Jupyter notebooks, the open notebook we're going to be talking today mostly. So the idea of the Jupyter is that you can write your code in a web browser. You can have the kernel running your computation somewhere else, in the cloud, in Amazon, in your lab, whatever, and then you get the computations back through your browser again. But with this new architecture, the language was not limited to Python. Actually, Jupyter stands for Julia, which is a computational language for doing calculations, Python, which is a general purpose language for almost everything, and then the R comes from the R language. So in Jupyter, you can have flawlessly working with the three of them, and there are many, many, many more kernels that we'll show later on. And then the explosion happened. So Apache hosted one of the projects called Zeppelin, which is a polyglot notebook, able also to run and execute code in a variety of different languages. We have the Jupyter notebook, which was formerly Ipython. We have a thing called Jupyter Lab, which is probably the future version of Jupyter is going to be all Jupyter Lab, which is not just one single notebook, but actually an IDE, an integrated development environment. Mozilla did something super cool called Iodide. And Iodide is especially cool because it doesn't need a kernel running somewhere else. It executes your Python statements in the browser. It uses like a technology called ASM, I think, which is a superset or a subset of JavaScript, super highly optimized. So it translates the Python code into a version of JavaScript that can run natively in your browser and executes in the VM, in the virtual machine of JavaScript in your browsers, and then you get the result back. It's obviously a little bit slower because our browsers are not very well designed for that, but you have the computation, the running, the execution, and the print in the same environment all together without the need of setting up anything extra. SageMath has been in the game for a while now. They were also pioneers in the Python ecosystem of notebooks, but they, instead of making their approach minimal to the existing libraries, they created a lot of glue code to put all the libraries together. So there is NumPy, there is Panda, there is Matplotlib, which have different libraries in the Python ecosystem. And SageMath, even though their notebook is pretty amazing, they created a lot of different libraries, which you can only use inside of SageMath, making extracting and taking your code somewhere else a little bit more trickier. Now they're changing their mindset. We don't know, maybe it's a little bit too late for that. And then, of course, R Markdown, which maybe a lot of you know because it's the native version of notebooks in RStudio. When you open an RStudio thing, you can write Markdown alongside with your code, and that's called an R Markdown. It's basically a way of creating open research notebooks with R. There are also versions that are not open source, that are not libre. We have mentioned Mathematica, Maple, and MATLAB, but there is also SMath, Carbide, Databricks, which is a Californian company that made their own re-implementation on top of Jupyter. But because of the license of Jupyter is very permissive, they are allowed basically to resell it under their own terms with their own additions. They call it the Databricks Cloud. To be honest, it's very easy to use because you don't have to worry about the computation. You don't have to worry about the memory that your program is going to use. You just make a couple of clicks. You have an instance trigger up. Then you go to an URL, and then you start working with whatever data sets or whatever code you're working on. They take care of the rest. And then there is a thing called Observable, which is a creation by Michael Bostock, which Michael Bostock was the graphical designer of the New York Times. If you ever read the New York Times, whenever there is an interactive visualization, kind of cool with maps relating to text and navigation that scrolls down and changes and then pump a video, that was all creation of Michael Bostock, okay? So he saw an opportunity and then created his own version of literary programming, but only and exclusively in JavaScript. The main advantage of this is that the programming is reactive. That means that whenever you introduce a new piece of code, that piece of code is affecting to everything that is referencing it. For example, I create a variable, and then I modify the variable at the end. Everything that depends on that variable is going to change magically, just because of the reactive nature of Observable. As opposed to, we'll see the Jupyter notebooks in which you only execute a cell, and then if you want more execution, you need to execute another cell. At any point, please, if you have a question, just let me know. But why Python, though? Why Python is now so popular solely for the formatting? I don't know if I can fix it. There you go. Well, Python has been rising since the last 10 or so years. Depending on who you consult with, they will tell you that Python now is one of the most popular, that is rivaling Java, that is rivaling C, but the reality is that it's one of the most popular languages right now. So Python was a natural choice. Also, Python has created, well, not Python, the community of Python have created a lot of libraries for doing data sciences. And if you go, for example, to the Kaggle Machine Learning and Data Science Survey, Kaggle, it used to be an organization that people could create challenges in. A challenge is composed of a data set and a question. So for example, there was a challenge in which you have photos of Antarctica with seals laying down and sleeping, because the color of the skin was very, very similar to the color of the rock. The challenge was to count how many seals were found in those images. So they proposed a challenge in coalition with, maybe it was National Geographic or NASA, I can't remember. So they released all the data and then said, okay, whoever makes the most performance algorithm to calculate how many seals are in this data set is gonna win, I don't know, $10,000. That's a challenge. After the years, Kaggle was acquired by Google, obviously, and recently they ran a survey to see what tools were the most used globally in all the challenges they have been running since they started. And at the top, way ahead of everything else, Python is the top programming languages data scientists use to solve data science problems. And of course, the digital humanities. This is a study just published like a few days ago by Lotte Borbot and Frank Fischer and others. They use the list of tools in taper.ci, which is a repository of listing tools, to extract the occurrences of those tools in the abstracts of the different editions of the Conference on Digital Humanities, the global one, the world one. If you plot that information not by year, but by the number of occurrences and tool, you see that at the end line, right at the right of the chart, you see that Python is also one of the most cited tools in when doing digital humanities. So it was a no-brainer. So one of the most used programming languages in the world, the one with the most rich ecosystem for doing data science, and also the language which is becoming more and more used in the digital humanities. So what is Jupyter then? Well, as I said, it's basically an open source research tool that can help you to write not only code that you want to execute, not only part of your analysis, but also can help you document how you reached those conclusions, why you made those decisions, and what are the dead ends, for example, in your research. The name, as I said, comes from Julia, Python, and R, but there are more than 40 programming languages supported. That's the logo of Jupyter, which tries to be the planet Jupiter and 3 of the moons, but Jupiter have like, I don't know, like 20 moons, so maybe it was a bad choice to model your logo on something that has 20 moons. And this is an analogy that I really likes. It comes from the software carpentry and data carpentry. How many of you know the Carpentries initiative? Maybe they are not so popular here in Europe, but in North America, they are trying to fill the gap between researchers and tools. So they have programs running, they have institutional associations with universities. They go to the place, and then they give you a workshop on whatever specific tool you need, ranging from Pandas, which is the Python analytical tool for exploratory science, which ranges from Pandas for ecology to natural language processing, for libraries, uses of Python. They have a very, very rich curriculum, and all the materials are free to use. Some of them are either CC0, which basically means they are in the open domains, in the open domain. You can do whatever you want with that material, but still, it's good to cite them, especially if you're using their materials. This is an analogy they make when they try to teach an introduction to Jupyter, that you have your field notes, your little notebooks when you're on site. So now you are going to translate that image to a notebook, which looks like this. Based on the literate programming approach by Donald Nutt, Fernando Perez, the guy behind Ipython and Ipython notebook, and then the thing became Jupyter, coined this term called literate computing, in which it's basically the same thing, but you store in a literate document format the results of these commands along with the figure, the free text form that can include formatted mathematical expressions. And that's really important because you can embed Markdown, which is a very rich format, a very rich language that allows you to format documents. I'm fighting against the mic. I don't know where to put it anymore.
You can put this place yeah.
Okay. All good?
Yes.
Maybe I need one of those, like a pop star or something, so I can move around. A gold one. Exactly, a gold one. Sorry, so the idea of the literate computing is extending a little bit the literate programming to also include the result of your computations. As literate programming only stops at documenting your choices and the code, literate computing also includes the results of the computation. It's not really that much of a super great idea, but it was a very crucial aspect that made notebooks very widely used these days, because it's not only that you can see the mental process of the person behind the notebook, but also the outputs that person got, which make reproducing his or her results much, much easier. In terms of the architecture, Jupyter, it's composed of two parts. On one side we have the front end, and then on the other side we have the back end. Those are very techy terms used in the industry to refer to the way in which websites are usually built these days. When we say front end, we basically mean things that are run in the browser by the browser. Everything that runs in the browser is called usually front end. Everything that runs in a server somewhere else is called back end. So on the front end side, we have the web application, which is a browser-based tool for the development of the actual notebook document, and then the notebook documents, which is each individual instance of a notebook. We can see that as a single page, for example, in a notebook. Internally, all these notebooks are stored in a format called JSON, which stands for JavaScript Object Notation. It's just a serialization format. You can have things in plain text, you can have things in XML, but you can also have things in JSON. JSON is a very popular serialization format. There is also even a superset of JSON called YAML, which is very common these days as well. And the thing is that each of these documents, when you made a Jupyter notebook, is stored as a file with the extension IPYNB. If you open that file, what you'll see is a JSON format file. It's something that you can mostly read, but in the end, it's intended only for renderization and interpretation by the notebook server. On the back end, though, there are two parts. One is the notebook server, and by that I mean the system that is providing you with all the interactivity that the front end needs, is making all the connection, is communicating through WebSockets and everything, and then there is the kernel. And the kernel is the part that actually makes the computations. When you run print 1 or 1 plus 1, and you click enter, we'll see that little statement is communicated to the front end. The front end takes that, serializes into a format, and then using WebSocket, send this to a notebook server. The server receives it, and then send it to the kernel. The kernel makes the computation, gets the results back, and then all the way up the chain until the user can see the result. Very schematically, this is how the architecture of Jupyter is designed. So if this is the happy user, super happy to use notebooks. he goes to a browser, and then the browser is showing a notebook server. The notebook server is able to read notebook files, which are ended in I, pi, and b. And then whenever a computation happens in one cell of this notebook file, it's sent to the notebook server, and the server communicates with the kernel. And it's the kernel, the part that actually makes the computation. At its core, Jupyter works basically as a front end to Ipython. If we run this little piece here, this is already a notebook. These slides are a notebook, but I made them in a way that they can also be rendered as a slide presentation. But the good thing about using a slide presentation made out of a notebook is that you get the interactivity in your slides. For example, this is a little snippet of Python that I made just to show something, file, open new terminal, and then a link to a terminal. So if I execute this cell right here in my slide, I should get the result back. And this is the result. Now, if I click here, I'm going to get off full screen for a second. If I click here, now I want to stay on the page. That's because I am on slide mode. But of course, you can get off the slide mode, and then you can click here. And this is still just Jupyter. Jupyter also provides not only a way to write your notebooks, but also a terminal and a very basic file manager. If here we write a Python, okay. This is basically the interface of Ipython. I can write a simple command, then press enter. So, and then it's waiting for more. That's a key part. Oh, you can see anything. Sorry, it says print here, then hello. So basically it's the most basic statement in Python, just printing something to the screen. So you see that there is an in1, so that's basically the input number 1. So I added a Python statement, so it's printing the string hello back to the screen, and then I get the result. That's Ipython. So Jupyter builds on top of that, but instead of using a terminal, it's using a web browser. Oh, it's fine. I'm not going to use the black screen anymore. Before I continue, I was just wondering how many of you know any programming language at all? Okay, quite a few. How many of you know Python? Coincidentally, almost the same people. I mean, that's good, so I don't need to be worried about introducing code in Python. You're at least somewhat familiar with the syntax of a programming language. So if you see a while loop, it's not going to surprise you. If you see a print, it's not going to surprise you, right? How many of you work with Python in your everyday? Okay. Have any of you, sorry for the questionnaire, have any of you done a research project using Python or any of the tools that Python provides for data science, data analytics, data exploration, natural language processing, computer vision, machine intelligence, sentiment analysis? Okay. Don't worry, I got you covered. So this is the REPL, okay? It's just a loop, read, eval, print, log. Internally, what Ipython does is that it has a while true, which is an anti-pattern. If you show that to my programming professor in college, it will give you a fail because that's something that you never do. But there are cases in which it's useful. For example, here, I want that input to be asked every time some code is executed. So a while true is exactly the while loop in here. So while true basically means all the time. All the time, whenever the user is entering some code, you store that code in a variable, and then you execute the code. That sits at the core of Ipython, and Ipython sits at the core of Jupyter. Internally, it's a little bit more complex because it needs to do things such as serialization. It's using a message queue, which is a software artifact that allows you to enqueue messages. So they are delivered sorted. So if you send a message queue is gonna guarantee that you're not gonna resolve a second message before resolving the first message that has arrived. So it basically guarantees that things are gonna be processed in the order they come in. Something very similar to the FIFO, first in, first out. That's what the message queue, in this case, 0mq, it's doing in the kernel of Ipython. And that way of thinking about structuring the architecture of Jupyter actually gave birth to the support for any language out there. So you can have, for example, a wrapper kernel in which you use everything all the way to the layer of Ipython, and then you just delegate the actual execution to whatever language you want to use. You can have, for example, a kernel that is executing Scala code or R-lang code. So you get all the way up to here, and then executing R, and then all the way down again to the user. Same thing with a native kernel. You can have all the machinery for the handling of JSON, all the machinery for the message queue, and all the machinery for the language execution itself. And that's the reason why Jupyter is so famous, because it supports many, many, many languages. This is a non-comprehensive list of all the kernels that are actually right now implemented as fully functional in Jupyter. I'm just gonna scroll down. So languages like Agda, which I don't know, APL, Fortran. Fortran is like thousands years old. Ansible, PySpark, all the versions of Python, Julia, Node.js, LiveScript, C#, Go. The list go on and on and on. So no matter what language are you working on, you're gonna be able to plug it into Jupyter. It's not only for Python, right? That's the key aspect here. It's not only for Python. It was designed for Python, Julia, and R, but you can plug almost anything. There is a kernel for Stata. There is a kernel for the Wolfram engine. There is a kernel even for assembly. And there is a kernel called iPolyglot that allows you in the same notebook to interchange code and variables between JavaScript, Ruby, Python, R, and many, many more. People just made those kernels. There is like a document specifying how can you build your own kernel. So if there is a language that is not supported yet by Jupyter, you can create your own kernel and put it out there, and people will use it, and you have all the niceties of a new language. And as such, the Jupyter ecosystem grew. At the core, we have the IPy kernel. Remember that after the Ipython changed its name to Jupyter, Jupyter split the project. They actually call it the Great Split when that happened, because in the GitHub repo, they created different repos. They moved issues. It was kind of a mess, so it took months to actually crystallize that split. And then the Ipython just became one of the possible kernels, the one that is shipped by default if you're using Python, but not the default kernel of Jupyter. This piece here, it was the original version of Ipython. Now it's just one of the pieces in the whole puzzle that is Jupyter. We have, we have the Python, which is communicating with the Ipython kernel. There is a way to have interactivity. There is the IPyMB format. There is a client. There is a call. There is a console. There is a Qt console, so you can even use the output of your computation, especially the graphical plotting, to show up in a window, in an external window, not in line in the notebook. You can convert your notebook to Latex, to PDF, to Markdown, to Python, to HTML. There are, on top of that, servers that you can use. This one is super interesting because it's intended for multiple users with no logins. They're not persisting the information. It's just to try. Just spin up a new TMP, MB, whatever server. You do your coding, and then you shut it down, and it disappears. It's not persistent. And all of this is open source. You also have the Jupyter Hub, which is a version of Jupyter with logins. You can have federated logins. You can have your institution have login gateway for the Jupyter Hub. So you log in with whatever university credentials you have, and then you go to a federated version of Jupyter. There is the viewer, which we'll see in a second. And this one, the MB Grader, is an add-on that you can use to grade activities. Let's say that you are teaching a class using Jupyter notebooks, and then you create activities. So by using MB Grader, you can check semi-automatically that the output of the students is the one that you are expecting. And it does that automatically. So it makes kind of easy to get a first idea on how students are performing. Of course, I am against automated assessing of grades, but if you are more like to it, you can use MB Grader. Questions you have? You can have, no? Okay. So as I said, there's been a considerable development, not only by the Project of Jupyter community, but by external collaborators. I showed you a kind of a map of everything that is going on. But what most people use is that they use Jupyter with some kind of version control of their files. They connect to different data sources. Can be local data, can be CSV or Excel files living somewhere else. You can connect to some sort of structured data like tags, or even connect to SQL databases directly inside your notebook. Then you get computations, you get the output, you get the explanations, and then you can print it back to PDF, HTML, Python, or whatever. And then that piece of that artifact can be embedded into books, wikis, blogs, email, whatever. There is actually an initiative by O'Reilly. O'Reilly is a publisher of technical books. It's the one that always puts an animal in black and white in the cover page, in the front cover page. If you ever see the Python book, which is like this thick, it has a lotus, I think, a lotus, the animal lotus, with the big eyes. And then you compare that to the one of JavaScript, and it's like this thick, so there might be something going on in there. So they are trying to get their authors to edit and to create books explicitly and uniquely using Jupyter notebooks. Yep.
So Javier, could you just repeat the name of the publisher? Was it O'Reilly?
O'Reilly, yeah. It's O''. O'Reilly. Maybe not really. that doesn't sound quite right. But if you Google is gonna fix the mistake for you.
Yeah, thank you.
Now I'm intrigued. Oh, really? There you go. Call O'Reilly. Not this. Like that. There is some people like, let me show you, maybe I have it somewhere here. Notebooks. O'Reilly Media. Embracing Jupyter Notebooks at O'Reilly. That was 2015, so a lot changed since then, but still there are books that are made entirely inside of notebooks. And then they export that as a PDF, they compile it together and publish it, which is very, very, very handy for authors and for researchers. And there is this guy, his name is Jake van der Plas, I think. Jake van der Plas. Jake is an astrophysicist, but he's also an advocate of open science and using Jupyter notebooks. He releases a lot of his notebooks for research. He has workshops, books, sessions, all about Jupyter, how can you use Jupyter. He is one of the maintainers and creators of Altair, which is a plotting library based on SVG, if I'm not mistaken. And also he has a book on data exploration using pandas, which is the exploratory library for exploratory analysis library in Python. And in summary, everything he does is great. I don't know how these people do so much work. Oops, don't know. A second. Okay. So in summary, Jupyter notebooks are great because they allow you to document your mind process. You can combine narrative in textual form. You can combine your concepts, your ideation process with machine executable code, all in the same place. And also it allows for exploration and development because all the steps are stored and all the outputs of all the steps are stored in the notebook. So it's easy to go back and see where the mistake was and then redo it. So it's easy to track all the changes that you have done in one single notebook. It's also great for communication and collaboration because you can share your notebooks and people can download a notebook and execute it locally in their environments. But it's also great for publishing. As I mentioned before, even big publishers like O'Reilly is making use of Jupyter notebooks for publication. But you can also, for example, have a blog made entirely of Jupyter notebooks. You write your post, and then you want to embed some kind of code in your post. So you write your code, you get the execution back, you show the results, and then you convert that notebook into a static page, and then you put it in your blog. There are actually people who use Jupyter as their editing tool for writing a blog. Questions so far? No? Back in July of this year, 2019, the team behind Jupyter, with Fernando Perez included, published in the PLOS Computational Biology Journal an article called 10 Simple Rules for Writing and Sharing Computational Analysis in Jupyter Notebooks, which is basically a recipe of 10 tips that they give you to make your notebook reproducible. They propose this kind of cycle. So the idea is that first you start by thinking of a story that you want to tell, by thinking a narrative that you want to tell an audience. Then you document the process, you add divisions in your notebook, you can have headers, different sections, you organize all the documentation, then you work with your code, you track all your dependencies, you use control version systems like Git or Bitbucket or Mercurial. We'll see about that. If too big, you can modularize your code. You can create libraries. You can create little snippets in files that make use of a chunk of code that is probably too big to document in a notebook. If everything goes well, you can even build a pipeline that is easy to parameterize. That means that you can create a pipeline and then allow other people using your notebook to execute it entirely just by changing a couple of parameters. Then you design, share, and explain everything about the open data, the interactive nature of the code. And if you feel like, you can advocate for using this kind of methodology, and then you read, run, and explore, and back again. The rule number one, as they define, is to tell a story for an audience. So it's not just what you did, but why you did it. And the story obviously depends on the audience. It's not the same thing to write a notebook for teaching a class that to write a notebook that is going to become a book. But the most important tip here is that the audience, it's going to be always your future self. Because no matter what, it's very likely that in the future you're going to go back to that notebook. And I don't know about you, but I have a very bad memory. So code that I write today, I'm not going to know exactly why I wrote it that way tomorrow. So it's a very good idea to document the process, all the decisions you made to reach that conclusion, and to write that code, because it's going to help you in the future. Document the process, not just the result. Make sure to document all the exploration. Now that's very important because some of them are dead ends. Still, if you don't document all the dead ends, you are destined to replicate them again, losing time, losing energy, and losing resources. And of course, don't wait until the end to document your process, because when you have already 100 cells of code, it's really hard to go back and start documenting everything. Just document as you go, try to be clean, organize, and annotate all of your cells in the notebook. Sometimes, one idea related to this is that for certain kind of publications, they ask for camera-ready versions of your paper. For those papers, usually you have to produce images of a specific quality. I don't know, like 300 PPIs, black and white, grayscale, full color, whatever. If you are making all your computations, all your research based on a notebook, try to make that notebook plot the images camera ready. Because if you use a different software, let's say that you print a part of the plot and then you use Photoshop to add a fancy title and whatever shades on the bars, then your notebook is not going to be 100% reproducible, because it doesn't take into account the process that you have done externally of the notebook, in this case using, for example, Photoshop. It's hard because plotting is usually always hard, and the libraries for plotting in Python are not as neat as the one in R, but still it's worth the effort.
Can I ask you something?
Yeah.
Documentation of the code was a prerequisite even before, the open notebooks. Do you, as a researcher, do you add the formal, let's say, documentation in the code as well, like inside the code?
You can, if you want, you can do it, but it's an extra. It's an extra step. This is just, I don't like to say run and trash code, because it's not exactly that, but not all the code that we write as researchers is going to end up in a package library that others can use. Usually these pieces only work for one specific domain, for one specific library, for one specific data set. So that code might not have documentation per se. It's not going to have this function, take these parameters, outputs these, behave in this way. No. When I say documentation in here, it's about textual chunks of text that you add in between the functions, or even between the computations itself.
Yes, this was called documentation of the code, wasn't it?
Of the code, but not of the process. You are documenting your process, your mental process. You're not documenting that I created a function, I don't know, integrate. Function integrate takes a parameter integer and outputs or whatever. That's not the kind of documentation I mean. I use integration because I wanted to reach a conclusion about this code. It's a different kind of documentation.
Thank you.
Also try to modularize. I'm stepping on. Try to modularize your code by cells and label them as soon as you can. The language that is supported by default in Jupyter is called Markdown. I'm going to show you how Markdown looks like. So it's a plain text format that produces a rich HTML output. So for example, if you want to write headings, So you get the heading H1, heading H2, H3, which are standard elements of HTML that receive different treatment in terms of rendering. If you want to write a heading, you just write the hashtag. Well, now it's called hashtag. It wasn't like that before Twitter, right? You write one hashtag, you get the heading 1. You write 2, you get a subheading, and then you write 3, you get a subheading, stuff like that. If you want to embed code, you can also do it just using the backtip. You can even write latex like this, and then it will render beautifully as a latex equation using mathlex or mathlex, something like that. A JavaScript library that renders latex for you. This is how you embed code. This is how you create a table. So it's all plain text, but the output of that is HTML that looks and behaves like HTML. So this is the format that by default you're going to use to document the process of your notebook. Try to avoid long cells. Anything over 100 lines, it's prone to be split in at least 2 different cells. 100 lines of code is going to be hard to follow without proper documentation of what are you doing. If the notebook is too long, also try to split the notebook, always adding an index that is linking to all the different sections. If too big, modularize your code. Try to avoid duplicate code, wrap your code in functions. If it's too big, in modules, and then in packages and libraries. And if you really want to make a contribution to the community, try to make those libraries be compliant with the Python package index. The PyP, as is it called, PyP, is where all the Python projects are released. If you're working on a research project and you have a notebook full of code, but you feel that people can benefit from that code, you can modularize that code and create your own library. When your own library is ready, you can upload it to PyP, and then other people can import that library and use it. But this is a different workflow than using Jupyter Notebooks. This is for when you want to publish a library. That only happens when your code is generalizable enough, can be used by other researchers or by other people, and that's something that no one has done before. So you want to contribute your code to the community.
Who's behind this? Who runs this pipeline?
The Python Software Foundation. There is a foundation, international foundation, that runs and maintains all the index for all the packages. And the numbers are crazy. They have like billions of downloads. Well, they have like 2 million files. And there are many, many more downloads every day. They actually run fundraising. They have fundraising efforts because this doesn't maintain by itself, but there is a whole structure now.
It's a non-profit.
It's a non-profit. It's a non-profit. They used to have Guido van Rossum, one of, they call it something like benevolent dictator for life. Guido van Rossum. Yeah, they call it BDFL, benevolent dictator for life. And he's the creator of Python, right? Python was his master thesis project, and then the foundation gave this title, honorary title, to him, and because whatever he said was kind of okay, Guido, we'll do as you say, right? Now things have changed a little. The organization is more democratic in a sense, which is also good for the community. People can feel that their voices are heard, which is good. They have a system for modifying the language. You know that software artifacts are versioned. So you can have Python 2.7, Python 3, 3.2, 3.5. So if you want to make an addition or a change to the language, you can. It's totally open. You send a form called PEP, which stands for Python Extension Protocol or something like that. I can't remember exactly. And you fill the form, and then you document the changes you want to make. That goes for a vote, request for comments, and then if everything goes well, your contribution is made to the final implementation of the interpreter of Python. Since then, Guido van Rossum joined Dropbox. He tried to create a new interpreter for Python that is not limited by the GIL, which is an artifact that Python has that basically hinders your ability to run concurrently programs. But I think he's retired now. He retired this year, if I'm not mistaken. And I don't think that anyone is taking the role of benevolent dictator for life anymore. That was just one thing that happened then, and it doesn't replicate over. Part of the abilities or the capabilities of Jupyter is the option to show interactivity. There is a package called IPyWidgets that allow a user running your notebook to modify the parameters using visual controls. For example, a slider or a select box or an input box or a text box or a button. So you can write those commands for your computation. Let's say that you are plotting temperatures of different countries since there are records. So you can create a tiny control selecting the country or a tiny control selecting the year, and then you write your function to do the plotting, and then the user that is running your notebook can modify the output by tweaking those controls. I'll show an example of that. Well, maybe we can see an example in their page. Or maybe not, because their page is kind of horrible. This is the thing. You write a function that basically does nothing, and then you say, okay, I want to interact with that function. And when you run that cell, you get slider control like this. That is modifying the value of x. So every time you change the position of the slider, f is invoked with the new value, and the result is printed back to the screen. So if I move this slider to the left, I'm going to get values for x, for example, 9. Then f will be evaluated with an x that equals 9. It will execute the function, and then I will see the result. Of course, that is extendable for any kind of data type. You have booleans, you have a string, you have integers, you have whatever kind of data you want. Dependency. This is very, very, very important. Record your dependencies. Not only the software packages that you're using, but the version. Sometimes you start doing some research, and then you say, okay, I'm going to use Pandas version 2.3 because it's the one that is released right now. You write all the computations, and then 3 months later, the Pandas people decide to make a change that is not backward compatible. That means that they have made a change that might break your code, making it not reproducible. If you don't pin your versions, that problem might happen to you. So it's a good idea not only to list them and track them, but also to pinpoint exactly what version is your notebook using. For that, there are 2 ways of going about, depending if you're using pip or conda. We'll see exactly about that. Pip, what it does is it searches packages in here. If you want to use a package that is listed here, for example, random blank. Let's say that I want to use this package. So I will use pip, which is a command line tool, and then I will go pip install runtime. It will go to this index, download the package, and then it will install it in the environment. So I can use it, all the functions defined in this specific particular library. That's using pip. But Python historically has been really hard to install. So there is this company that makes a Python distribution called Anaconda. I don't know if that sound rings any bell. So Anaconda makes its own PyPy, so to speak. They have their own index, because sometimes Python needs to access C extension libraries that need to be compiled, and it's a pain to have your system set up to do the compilation because it's very time consuming. And they have pre-packaged, compiled versions of some of the libraries that they have it in their own registry, in their own repository of packages. So when you use Conda and you run a Conda install, it's not going to Python. It's going to the Conda repository to see if the software package is there, and then download it and then install it. Sometimes you might have differences in behavior if you install one thing with Conda versus with pip. Whenever possible, try to use pip, because Conda in the end belongs to a company. Companies can come and go, can make whatever political decision they feel like, might disappear, might make the repositories suddenly private. We don't control private companies, but we can trust the foundations that run Python at least. If you're using pip, you can list your requirements in a plain text file called requirements.txt. If you're using Conda, you can export an environment in the environment.yaml. This is an example of the environment that I'm going to be using today. These are the packages that I'm using for this presentation. Obviously, I'm using Jupyter, Rise, Request, Pandas, Voila, NLTK, whatever. The mistake here that I made is that I'm not saying, hey, use Jupyter version 3.0, use Request version 0.7. I'm not pinning the version. So in the future, if I want to rerun all the execution cells in this repository, I might face some troubles because I'm not pinning the versions. Oops. One useful extension, because Jupyter also allows for extensions, is watermark. If you use watermark, which we'll see, it's just one kind of specific statement that only Jupyter understands, that you can install, and then you say, okay, watermark, and tell me the version of NumPy and SciPy, and it will print down a nice summary of all the versions of your interpreter, of the kernel, your system, and the versions of the libraries that you are using. So even if you are not pinning your requirements, you can still display that information inside your notebook. It's not the recommended way, in a sense, but at least you are not losing that information. This is an example, okay? So here I'm just installing watermark. This is a cell execution. I'm reloading the extension, and then I'm saying, okay, watermark, print nicely with some parameters, the versions of Request, Jupyter, NumPy, Rise, and Pandas. Then it should have printed all the versions of the libraries that I have listed. Okay? Use any kind of system for version control. Jupyter, underneath, is using JSON, which is plain text, which is versionable. That means that if you make a change in the JSON file, it's going to be the Git or the version control system that you're using is going to be able to tell you what's the difference between the version of today and the version of yesterday, which is also pretty useful. How many of you know Git or Subversion or GitHub? It's very likely that you know GitHub without knowing Git. But that's totally fine. They are that good. Well, GitHub is just a front end for Git. Git is a control version system. I think it was created by Linus Torvalds, the creator of the Linux kernel. The idea of Git is that everyone in its machine can have all the history of the versions of his documents. Okay? Git works pretty well with plain text files because it has a diffing tool. A diffing tool is just a tool that it allows you to visually see the changes between two lines of code or text or whatever. For example, let's say that you have a function and then you decide to change the name of the function. By diffing, you will see that you have added new characters or that you have removed those characters. and every version that you save with Git is stored forever. So if you ever wanted to roll back because for whatever reason what you have done is not working, it's like a Control-C, a magic Control-C. You can go back, as long as you save it, you can go back to whatever revision of your code was working. GitHub is just a front end for Git, but it's a front end that works so well that everyone basically is using GitHub right now for almost everything. But underneath GitHub, what it has is a wrapper of all the Git functionality. However, although Jupyter uses JSON serialization, which makes this impossible, the format, it's kind of tricky, and it's not that easy to visually see the differences. For that, we can use a tool which is called NVDime, that it will pop up, open a browser, and it will show you, okay, this line has changed. It will show you in red things that have been deleted, in green things that have been added, and then you will see what lines have changed, what lines have been edited. It's very important to use version control. If possible, build a pipeline. That's just like going one step beyond. Let's say that you have a workflow, you are analyzing a specific data set, you make a workflow for that, you have all the workflow documented, you have 3 or 4 parameters that you need to set before running the entire workflow, but you realize that your actual data set is not only 1 file, but 1,000 files, and you want to run exactly the same notebook on the entire data set of 1,000 files. For that, you can parameterize, you can make, you can tell Jupyter to use parameters. So you have your notebook written, and then you say, okay, this, and this variable are going to be my parameters. So whenever I run this notebook with new files, I'm going to be able to change them, adjusting to whatever files new are coming, making your notebook essentially as a script that you can that you can run and passing new parameters. That's probably going one step beyond. The natural thing to do after that is guarantee code quality. There is this thing called continuous integration in software engineer practices. They basically try to guarantee that if you're working in a code base, for example, let's say that you are part of a team and then all the members in the team contribute code to the same repository, and then all the files are using functions defined in other files. There might be the case that one member of the team write a function that breaks everything, right? So to alleviate that problem, continuous integration came into existence. What it does is that it tries to run a battery of tests against the functions. So if a new function is breaking old code, it's going to tell you. And it's not going to allow you to merge that new code into the working code base. That's the purpose of continuous integration. And by doing Jupyter notebooks as a pipeline, you can guarantee that no new code is going to break your old code. Travis is just one of the examples of a free for open source projects continuous integration system. If you go to Travis, this is, for example, Mirror, which is a IIIF viewer for images. And then you can see what it does. It does a lot of setup, and then at some point, it starts passing tests. It's running tests on this file, on this file, on this file, on this file, and everything is passing. So the new code that I added is passing all the tests. So now I am allowed to push my changes to the main repo. If something fails here, it will show as red. Let me show you. There is no red. Here. The changes that this person made were making tests fail. So before pushing those changes to the main repo and breaking everyone's code and execution, the continuous integration system raised an alert. and say, hey, I'm sorry, your tests are not passing with the changes you made. You need to correct that and then push again until the continuous integration system is not showing the green flag. That means that your code is going to remain the same. And this kind of system integrates with GitHub. So it makes the entire workflow works very flawless. I'm not going to talk a lot about how to share and explain your data because you know already almost everything that you need to know about fixtures, Zenodo, permanent identifiers like DOI. But it's always a good idea to have a publicly available version of your notebook. If you can even get a DOI for that, that'd be great. Zenodo can work with GitHub. You can even tell Zenodo to, I don't know if Zenodo can create a tag using Git of your code and get that artifact and put it as the artifact in the Zenodo. So it's pretty easy now to communicate GitHub code with Zenodo. Finally, for reproducibility expectations, you should be designing your notebooks to be read, run, and explore. It's always a good idea to add a Readme file. That's standard common practice in software projects, to add a Readme file. What is this repository of code doing? What does it have? What each of these parts are actually doing? What is the description? How you use it? All those pieces of information go into a Readme, and then pick a license. Pick a license that is actually open enough so other people can use it. For example, here I added a link to all the open source licenses that are created and defended by the open source initiative. In the case of this repository, we can see the license that we are using here, which is the Apache license. That's the one I picked. You can use MIT, you can use BSD. There are licenses that allow you to use whatever piece of the code without sharing it alike, which is kind of mean, but it's also possible. At least it's important to pick one license. Software licenses are just a mess. But if you don't have one, you're not protected in any way, so at least pick one. There are historically, there have been real legal fights against the terms of licenses. I remember one between IBM and a software project that they claimed that they added part of the code into the main code base of IBM. They were litigating for years and years, and then in the end, they gave the reason to the small piece of software. So it's really crucial to have a license, whatever it is, but to have it. An option, besides the README of the license, is to leave a static version of your notebook. It might be that software changes. It might be that the packages that you use are no longer available. It might be that the computational environment, you cannot use it anymore. So to avoid that problem and that people lose the ability to read your code, try to keep a track of the PDF or HTML conversions of your notebook so people can read it. You can even use an MB Viewer, which is able to read the JSON file of the notebook to render exactly how your notebook looks like inside a Jupyter notebook system. If you want to be able to allow people to run it, there are options. For example, there is Binder, which provides a zero install environment. You basically click a button, goes to the cloud, spin up a Docker instance, install all the dependencies, download your notebook, and then run it for you. You don't have to do nothing. It's free. It's supported by Google, OVH, DigitalOcean, I think, a number of hosting companies that see that this is a need. So they are basically giving for free computation time and credits to this initiative, so people can read and execute existing notebooks. Or you can create just a portable containerized environment. So the good thing about Docker is that the Docker is a way to create an environment that contains everything that you have done. It's a It's a thin layer on the operating system. So you can install things at the operating system level, and then install all the dependencies, including Jupyter, and then install also your notebooks, and then you can get all of that, package it in an image, and then push it to a registry, or share it with someone else. So everyone, no matter what operating system they have, will be able to reproduce your code using a Docker image. And finally, try to be explore friendly. Consider using Python widgets, like I showed before, or even consider using Voila. Voila is a Python extension to the Jupyter notebook that it will run all your code, and then it will hide all the code blocks, and only show you the outputs and the explanations, making some sort of interactive research article out of your notebook. We'll try to see an example of that. And finally, if you feel like, try to advocate for open research, try to teach people who doesn't know enough about Jupyter, try to use Jupyter whenever you can. There are other notebooks, not everything needs to be Jupyter. Questions? Has everyone downloaded the Anaconda? Yes? So I want you to open Anaconda. Now we're going to start with the hands-on part of the workshop, so no questions. Good. So when you open Anaconda, you see something like this. That's the first screen you see. Something very similar to this, right? What you have to do is click on Launch. When you click on Launch, I already clicked, so I'm not going to click twice. A new tab in your browser should open with something similar to this. Excuse me? Okay. Okay, we're done with the theoretical explanation of Jupyter. Now we're going to start the hands-on practice with the notebooks. So everyone has Anaconda installed and open. The main window of Anaconda is showing Jupyter Lab and Jupyter Notebook. We're going to launch the Jupyter Notebook.
No, because I can't download anything on this.
Oh, you didn't download it before coming here.
No, I'm not allowed to download anything.
Oh yeah, that's like
I'm
the
not the
problem
administrator.
for institutional computers.
Oh.
So I need a permission, which I don't have.
Okay.
Anyway,
Don't worry, I got you covered.
yeah, I follow there.
Don't worry a bit. If you go to the repo, which is show here, let me just open. So for those of you, actually for everyone, if you go to this URL, can you see it? So github.com/Versailles/open research notebooks. If you go to that address, you should see the repository page in GitHub for all the materials of this session. Okay? So you should see something like this. If you are running Anaconda locally, if you are not limited by whatever permissions, if you have Anaconda installed, I want you to download all the materials as a zip file. In the green button, there is clone or download. If you click on it, There is some weird options here for cloning whatever, and then there is a download zip. If you download the entire repo, it should ask you where you want to put it, and then let's say that I don't want to save it, and then you extract it, and you put it somewhere. I don't care. You put it in your hard drive, somewhere that you have control over. When it's done, if you're running Anaconda, again, locally, if you have the Anaconda window, and you have click on the launch button of Jupyter Notebook, no lab, not for now, just Jupyter Notebook. You click on launch, you should be able to see something like this. Okay, with all the folders of your hard drive, okay? So now you just have to navigate to the path in which you have downloaded this zip file. So from here, we have downloaded a zip file. We need to download it and unzip it and put those contents somewhere in your hard drive. So whatever that path is, I want you to go navigating to that address using this interface. So in my case, that was in projects, tons of projects, and then open research notebooks. If you have done that, now you should see exactly the same files that I'm seeing here. You should have a folder called scripts, 3 notebooks that you know they are notebooks because they end with the extension I, Pi, and B. In your case, they should all be gray, which means they have not been opened yet. And then a license file, a Readme files, a requirements file, a CSS, and a runtime TXT. Now, if you click, for example, in slides, you should see my slides, but as a notebook. Instead of seeing it like in presentation mode, you should see something like this. Right? So what we want to do now is go back to the folder here and then open the overview. So go back to the tree of folders and files using the Jupyter tree of files, and then click on overview. It looks the same because the first 2 cells are the same, but if you see the name, it's different. Now, if you go back to the same display of files, I have overview with a green book icon. That means that the file is open and there is a kernel waiting for my inputs. Okay? If you don't have Anaconda running, because whatever permissions in your machine, because your institution forbids you for installing stuff, you can use Binder. This repository is reproducible. Everything I'm showing, you can do. So you can decide whether you want to open each of the different notebooks we're going to be covering today in the notebook, in lab, or even in Google Colab. Google Colab, it's an implementation of the Jupyter notebooks. The thing is that it's their own implementation. So even though they provide things like GPUs, which is very nice when you really are in need of computational power, they do not implement everything we have seen. The other option is Binder. If you cannot run locally Anaconda, just click here. Oops. It says launch Binder. And that will open the entire repo in an instant in the cloud, free for you. If you click it, you're going to see a lot of weird stuff happening. Because it's taking the repo, which is in GitHub, here, which you can see here, which is exactly the same structure of folders that we saw before. It's going to take the repo. It's going to create a Docker image. It's going to take my requirements file. It's going to start installing one dependency after the other. And when everything is done, it's going to invoke the Jupyter command. It's going to run that into a server. It's going to give me a URL. That's a long way. It's going to give me a URL, and then I'm going to access to a web version of the notebook. Okay? I don't want you to know everything that is happening. I just want you to know that if you click there, you're going to have exactly the same thing that I have locally. That's it. The only difference is that in my case, because I'm running Anaconda locally, I have local host. It's my local machine running Anaconda. If you're using Binder, you're going to have some weird stuff like Hub, Google, Kubernetes, whatever. ¿Vale? I mean, okay? It's exactly the same thing. Now that you have the repo open, you can run all the notebooks. So let's start with an overview of what is exactly that you can do in a notebook. You can click on Overview. We've covered slides. Now we're going to go to Overview. You can either go using Binder, or you can either go using Anaconda.
Yeah, locally, how do we get to this path that you are?
Here,
Yes.
when you are in the Anaconda Navigator main window,
Yes.
when you click on Launch,
Yes, done that.
it should have opened
Yes.
a browser window with this address. It will not show this specific tree. It will show you your hard drive.
Okay.
In this case, this is my hard drive. Now you need to navigate to wherever you downloaded the zip file.
The zip file of what?
The zip file of the repo. I'll show you in a second.
Put it somewhere.
I'll
The
show you
second link to that Markdown.
here. So if you go to this address,
Okay, yes, okay. From GitHub, yes?
yes,
Okay.
from GitHub. If you go to that address, you will see something like this. And then if you click on the green button, clone or download, our contextual menu opens up. At the bottom, there is a download zip. You download that to your hard drive, and then you unzip it. You extract the contents. You put it somewhere in your hard drive. That's the location I want you to navigate using the Jupyter interface. You can just put it in downloads, and then just go to downloads, and then whatever is in downloads. Oh, this is the Michael Jackson documentary. Creepy stuff. In my case, I have it in projects. This is my case. This is where I put it. Everyone should have a different path. And then open research notebooks. And then voila, that's it. Everyone is almost there? So when we open Overview, now we see that there are the same two cells. Okay, so we can do this in two different ways. I can do the slideshow mode while you do the regular notebook mode. So because it's easier to follow when letters are big, but it's exactly the same. If you don't want to see all this slide type weird stuff that is only available when you are going to present to an audience, you can go in View, I think, Cell Toolbar, and then click on None. And then it should hide all the controls for the slideshow. Something like this. I repeat, View, Cell Toolbar, None. And it will hide the controls for a slide view. Okay? I'm gonna make this a bit bigger. I'm just gonna hide the header. So, at this point, you all should have Anaconda running or Binder running in the cloud with all the requirements installed. If you have not installed the requirements and you are running your own Linux box, so you don't have Anaconda and you are doing everything manually and locally, you then need to install Jupyter, okay? In either case, you can still install all the requirements in a code cell. This is a Jupyter notebook. The Jupyter notebook mixes content like this. When I click, and then there is a thin line surrounding a piece of text, that's a cell. That is called a cell. There are different kinds of cells. Textual cells are intended to render textual data in Markdown format. For example, this is not editable, but if I double click in a cell, I get access to the actual Markdown that is being rendered. So remember the one hashtag was header 1, 2 was header 2, and 3 was header 3. So I'm saying, okay, Jupyter, I want to render a header 3 with this title. I'm going to write this text here, and then I'm going to use a Markdown format for this specific link. If I want to see how the thing looks like, I have two options. Either click Control-Enter or click on the Run button. If you click on the Run button, boom, you should see the result of that Markdown code rendered. That's what I've been using all the time, just Markdown text rendered by Jupyter. Yep.
Speaking of Markdown, is it to some extent interoperable with Atom, or those are completely different?
I don't know, Aether,
Okay.
what that is?
It's Markdown editing kind of.
But it's only for Markdown.
Okay. Yeah.
I don't know, I'm asking.
Yeah. Yes.
Oh, okay.
As far as I know.
No, I don't think so. I mean, you can edit things in that editor.
It's a text editor.
Oh, it's a text editor, okay.
Yeah, Atom.
You can, but then it's hard to integrate into the notebook.
Okay.
There are ways, but it's not really it's not really easy.
Okay.
As I said, we need to install the dependencies now. So just to make sure that we all have the dependencies installed, no matter if you're using Binder, or if you have Anaconda, or if you're using your own local Linux installation. By running this cell, I'm just saying, okay, the requirements are located in this address over here. If I copy and paste that into a browser, if Firefox allows me, I get the list of my requirements straight from the repo. So I want to install those. So I just need to know, okay, I'm going to put that URL into a variable and then say pip install this file of mother of catch. Pip install this list of files, okay? If you run that, you should see something like this. If you're using Binder, you will see requirement already satisfied for all of them because Binder has installed them. If you're running Anaconda locally for the first time, you should see something like downloading, and then at the end, installing. If they're not installed, they're going to take a little while. But that's fine. There are not that many. For launching the notebook in a terminal, you just need to type Jupyter Notebook. A terminal is the black command line box that I showed at the beginning. Only for those who are who are using a Linux machine or a Mac OS with terminals, and they're very used to using terminals. If not, same thing, an Content Navigator, a launch, but we are already there, so we don't need to do this anymore. The other kind of cell is the code cell. As I said before, there are at least two kinds: the narrative with Markdown cell and the code cell. So for example, this one is a code cell. You can see the difference because I get an input tag in here. When you click in a text cell that is just Markdown text, there is no input because it's not expecting anything from me. When you click on a code cell, you'll get the input. If you run it, you can again press Control Enter, Shift Enter, or directly click on the Run button. You should see the result. Okay? Again, what's happening here? So it's taking that text, it's serializing that text, it's sending it through the 0MQ message queue, it's reaching the notebook server, it's being sent to the kernel. The kernel is executing that Python code, and the output is sent back all the way to the browser. And that's what I see here, the hello world. Okay? This is the typical program that everyone writes in every programming language ever, hello world. There is even a web page that displays different hello world programs for all the languages in the world. And there are languages very weird. Same thing for the narrative on Markdown, as we saw before. If you double click on a Markdown cell, and then you want to see how that actually renders in HTML, you just need to click the Run button. You can change the type of a cell at any time. Let's say that I want this cell now to be code for whatever reason. You go here, and then instead of Markdown, click on code. And then immediately you get the input sign here, and then the format has changed too, because now it expects code in this cell, not Markdown text. But this is a textual cell, so let's put it back as Markdown. We click on the select box, then select Markdown. And that's it. Now I wanted to execute it, so I click on Run. For example, yep.
Another question.
Yep.
So the notebook actually it has something like what you see, what is what you get editor embedded in.
Yep.
Yeah.
A very, very basic one.
A very basic one.
It's not that much, because what you're writing here is the format of Markdown. Still, you get bold, you get italics, but that's pretty much it. If you really want to see the result, you need to run.
Yes.
You need to run the cell. To produce this cell,
It has to do with the language, though. Yes. It has to do with because of Python, because it's something that is being built by Python.
no, this is by design, because the
Okay.
people in Jupyter decided that they wanted to run textual cells like that. There are extensions to Jupyter that you can use to get a proper YCY editor, if that's what you're looking for. But by default, it's shipped with this, which is the most basic version of the editor. So to get this text here, we have a header, then we have a couple of lists embedded, we have some text emphasized, and some with strong, bold, emphasized. We also have some code in here, and you need to pay attention here because this piece of code is not executable. It's just text that looks like code. It's formatted as code, but it's not executable. So to get that output, the Markdown equivalent be something like this. So a header, a header here, then text, then a list, then I want a nested list, a subheading, and then if I want to embed code only for the purpose of displaying a chunk of code, I use the triple backtip. If I want code inline, I use one single backtip. If I want a block of code, a chunk of code, I use three backtips. And that's defined in the Markdown definition. It's not nothing that Jupyter has invented or have decided. That's just the format of Markdown. Markdown can also include links, can also include images. For example, to render something like this, which has a link here, this link is actually to the DESIR school we are today. You can link elements in the same notebook, and you can even link elements in other notebooks. You can embed images as well. The format for links is like this. So you put the words between brackets that you want to be displayed. And then, right after that, between parentheses, you put the URL of the link you want. Compare that to the way in which HTML makes you write. DESIR Winter School, okay. This code over here is going to render exactly like this code over here. Actually, Markdown has support for HTML. You can embed a block of pure HTML, and it's going to render just fine. We can make a test. For example, in this cell, I want to add a link, so I just add a link using HTML. But if you don't want to use HTML because it's too verbose, you can still use Markdown, which is supposed to be a bit easier to handle. When you want to add an image, it doesn't matter if it's a local image that you have in your repo or an image for which you have the URL, it's exactly the same. You just add the image as a link, and then because it's an image, Markdown specifies that for rendering image, you need to put an exclamation mark at the beginning. It's just the way Markdown works. And then you'll get the image. If we don't put the exclamation mark, then we just get a link. That's just the way Markdown works. It's also able to render latex. So for example, if I want to render a latex expression in line, I just need to put the expression between single dollar symbols. So dollar, whatever expression in latex, dollar. That will be rendered like this, which is kind of awesome. But if you want your equation to be displayed in its own block and centered on the screen, you need to put your expression surrounded by double dollar symbols. If we see the code of this, it looks like this. This one is in line, and this one, it's block. It doesn't really matter what the latex is doing in this case. To select a cell, just click on it. Once you have clicked anywhere in the screen, you can move around with the arrow keys. Move up or move down. If you want to add a new cell, just click on the Add button. And this will add a cell below. If you want to add a cell above, you can go here and click on Merge Cell Above, or use the keyboard shortcuts. I'm very used to Jupyter, so I'd rather use the keyboards. So Control-M-A to add above, Control-M-B to add below. For deleting, you can also go Edit, Delete Cells, or Caret, or Control-M-D. And that's going to be removing cells. You can also move cells around. By clicking the arrows here, you can move the cell up or the cell down. So those little things are important because it's going to allow you to format and modularize your code. You can even split a cell. Let's say that you have a huge cell of code that you want to split, so you can put the cursor at a specific point and then go to Edit, Split Cell. And it's going to create two cells, exactly splitting in the point in which your cursor is. For example, let's say I have this cell, and I want to split here. So I can use the command line, the menus, or I can do it using the shortcut, which is Control split, Control split, there you go. Or you can also merge them, for which I don't know the shortcut. So let's go Edit, Merge Cell Below, and they're back together. Now, Control M, delete the cell. The outputs, and this is a little bit different from other notebook formats. So if I execute this code, the output is nothing because there is nothing to show. But if the last line, of a cell is a Python statement that is producing an output, you don't need to add a print to that expression because Jupyter is going to take that result and display it to you. For example, I have a couple of variables, A equals 1, B equals 2, and then I have a summation of both. If I execute this cell, I get 3 because the evaluation of the last line of this block cell is producing the result 3. So that's what I'm saying, which would be equivalent of doing something like this. Okay? You can run multiple cells up at a time. You can, for example, click Run a couple of times, and they're going to be queued for execution. For example, let's say that I have import time from time import time, and then I have time to sleep 5 seconds. Vayam. Now this one is queued for execution. So once the previous cell is done, it's going to execute that one. Okay, I'll show it again. I'm just saying, okay, execute whatever there is here, and then go to sleep for 5 seconds. So I'm going to execute this cell, and then immediately after, the next cell. So I click on Run twice. And then you see that there is a star here. That means that something is being executed. And then the little dot in here also turns solid. When I'm executing something, that little dot over there that you can see, it turns solid gray. That means that something is being executed. That's also a cue for when you have a very long notebook and you are running a lot of different things at a time, and then suddenly the notebook is not responsive. You have to look at the dot to see if there is something in your notebook that is being executed. As I said before, star in an input also means that it's waiting or executing, and they are in queue in that order. You can import packages as you do with Python normally. For example, we can import NumPy as aliasing the package as np, and then access to whatever functions NumPy has defined. And you can even invoke command line from commands from the command line. To do that, you need to add the exclamation mark at the beginning. That means run in my terminal this command. If you are running Windows, ls, it's not a command available in Windows. So for Windows machines, you need to comment out that by using the hashtag at the beginning. I know that this is a little bit overloading the meaning of the different symbols, because in Markdown, the hashtag is a heading, but in a code cell, the hashtag is commenting out a line. There is no way around. It's just the way it is designed. So if you have a Windows machine, exclamation mark, dir, whatever or whatever command, and it's going to execute that command in a terminal and giving you the result back. In my case, because I'm running on a Linux machine, I'm going to use ls, and then I get the result back, exactly as the terminal you have printed in the screen for me. If instead of just printing the result, I want those results become a Python variable, I can use the double exclamation mark and then put this into a variable, for example. If I print this variable now, oops, ls command not found. There you go. Now I'm saying, okay, execute this command in the terminal, get whatever that command has printed, transform those lines into a list, and then put that list into a variable. This is very, very handy for data science or for dealing with data sets, because there is a lot of commands that you regularly use, like grep, awk, set, sort, wc, commands that exist, that have existed for a long time in POSIX systems, that are very, very common. So you can use those commands in your terminal and then get the results back to your notebook. And that applies to whatever command you have in your terminal. Line numbering, when you have a big cell, can also be enabled. You just need to press escape L or command Control M L, and there is enable and disable line numbers. It really depends on your coding style if you want them on or off. They really doesn't do anything. And there are things called Ipython cell magics. So what questions you have so far? Yep.
Can I ask a question? I've had this question about Binder for quite a long time. When you run a Binder notebook, if you make changes to it, do you have to save it, and what happens when you?
They are
what
gone.
happens to it when you close it? I suppose?
They are gone for good.
They just go. Okay.
Yeah, spin up a machine for you. You can use it as long as you want, but if you want those changes back, you need to go back to your tree and then click on all of them. And I don't know if there is an option to download. No, you have to download one by one.
Okay, so you just download them. So
Yeah.
Because I was getting a bit subconscious working on Binder notebooks before, so I don't need to worry.
Yeah, Binder is great for reproducing other people's research, but not as a working environment for you.
Okay.
It's okay for this session, so you can just follow along, but not for your day-to-day work. That being said, though, there are installations of things really, really close to Binder that you can run in your institutional cloud. There is Azure Notebooks, which is persistent. There is Google Cloud, which also has support for persistent notebooks. There is Amazon SageMaker, which also have support for persistent notebooks. So it really depends. Or you can just spin up a machine in your lab, put Jupyter there, and then you're working, and that's never lost. We wish. To download, I think it needs to be one by one. Yeah. Yeah, it needs to be one by one. So you click on one, you download, you click on another, and then you download. I don't know why they don't add download all functionality. It's not really that hard. So there's also this thing called Ipython cell magics, which are also available in Ipython. And they allow you to do things that are not normally built-in functionality of Python. For example, there is an Ipython magic, and those things, again, only work on Ipython and Jupyter, to render plots inline. There is another to show all the variables that you have used in your notebook. This is similar to the variable table in RStudio, which is all the time present. In this case, you can print it at any time, but it's not always present. You can also print all the environments, variables that you have defined, for example. And some types of data also support rich output. For example, Pandas, the analytics library for Python, allows rich output. So when you print a data frame, which is the same concept in R than in Python, basically a table with columns and rows, you get some nice representation of a table, which you can even mouse over, and then you see the row. You can even format that to show threshold, to show different colors. So it supports rich output within Jupyter. In this case, we're just going to plot using matplotlib, 1,000 evenly spaced values ranging from 0 to 2 pi, which is basically a sine wave. And then you plot it using the plotting library of Python. If I wanted to add interactivity to that plotting function, let's say, for example, that by default, it's taking a value of f equals 1, and then I want to make that plot be interactive. The only thing I need to do is import interact from IPyWidgets, and then say, okay, make this function interactive. By default, pass a value of 5 for the variable f. You do that, and then you get the plot, render with the default value, but now we get a slider. And this slider we can change. And as we change it, the plot changes too. So I have written the plotting function once, and now just by adding a new statement, which is called interact, I get interactivity for my plot. Unlike this, any other function you can imagine for every kind of data. You can make your plots or your tables or whatever you want interactive very easily. For checking reproducibility of a notebook, for example, if you open this notebook in Binder and you just want to check that everything is working fine, you should go to cell, all output clear. So all the outputs of the code cells will be cleared, and then run all. That will run all the code cells since the beginning until the end. So you will see a lot of stars appearing in my inputs because all the cells are being queued, and then they are being executed one by one in order. If you need help while writing a Jupyter notebook because you don't remember something, there is always the menu help keyboard shortcuts, or there is a tour, an interactive tour of the user interface. There are links to the documentation of the most commonly used libraries, and there is also a meta character that you can use to see if an object or a function has any help available. For example, if I want to use a data frame from Pandas, I can use the symbol question mark, and then this will open the library documentation for the data frame function. Now I can see what kind of arguments takes in, what are all these parameters, what do they do, examples of coding, all within the same Jupyter environment. Of course, for this information to be displayed, it needs to be in the library in the first place. Another very useful tool of Jupyter Notebooks is saving checkpoints. For example, you are in a specific state, and then you go for a coffee. Let's say that in the way back, lights go off, and then your computer goes off, and you have lost all the work you did during the morning. So to avoid that problem, you can always go File, ¿dónde está? save and checkpoint. I don't know what the menu is. Oh, save and checkpoint, that is. You click save and checkpoint, and that's gonna save a specific state of your notebook in the hard drive. So if the machine suddenly shuts off, you still can recover and roll back from that specific checkpoint in time. It's usually easier just to click Ctrl+S. It's doing exactly the same thing, or clicking in the anachronistic icon of a diskette to save. If, for whatever reason, a cell is taking too long to run, for example, let's say that there is a cell that is taking forever, and I want to keep going, and I don't know what's going on. It might be the case that you have an error in your cell, that something is iffy in your code, but you just want to stop it. So you click on the stop button, and it will interrupt the kernel. It will interrupt the kernel so you can recover from the REPL loop, read, eval, print loop, and then you can start again. Let's say, oh no, it wasn't 10,000, it was just 1. And then you fix it. If everything goes super bad and then Jupyter starts behaving super weird, variables are weird, things weird are happening, just restart the entire kernel. Click on kernel, restart. That's going to restart the kernel. The outputs will not be lost, but all the variables in memory will be lost. So you will need to go again to the first cell in your notebook and start executing everything down. For exporting, just click on File, Download As, and there are many different formats that you can export. Beware, because for Latex and PDF, and I don't know if for HTML2, you need to have system-level libraries installed. In this link, it says that, for example, to get HTML export, you need to install Pandoc, and to get PDF with Latex in Windows, for example, you need to install MikTeX. If you don't have those things installed at the system level, Jupyter cannot export the things for you. Voila, it's the library I commented at the beginning. It's very similar to the Interact theme, but it hides the cell. It hides the code cell. For example, if I run this is basically a couple of sliders that make a multiplication, right? But if I have Voila installed and I want to expose this specific reproducible notebook to an audience or a community, I can make this notebook be served as a website, kind of like Shiny does for R, but in Python. So I click in Voila, which is here at the top of the cell if you have installed all the requirements. And then it's executing all the cells, one after the other, showing me the output and hiding all the code. So now I get like a website. Whenever there is some interaction, now that's just a slider that can modify. And the good thing about this is that it's publishable as a web. You can take this exactly as it is and put it on the web, and people can interact with your code. You can have a really interactive research notebook that you can share. Questions?
Sorry, the last step of the Voila, that went too quick for me.
The Voila thing?
Yeah.
Sure. If you have installed all the requirements, you should see a button here called Voila. There is the diskette theme, the Markdown, the play, the stop, a keyword, and then there is a Voila button. If it doesn't show up and you have installed everything, you need to close the notebook and reopen it, because for some reason it's not displaying properly. If you have that installed and you have created an interactive output using Voila, which by default is able to read the interact function that we saw before. It's just a matter of versioning. They are trying to figure out how to make it all work. In the notebook, I can play now with the sliders. But if I want to share this notebook only with the explanations and the outputs, that is, I want to basically write a research article that is interactive. If I'm using this component for interactivity, now after clicking on voila, I think it's here, you should see that it's executing things, right? That's basically running all the cells in the notebook, capturing the result, showing me the result, and if there is any interactive cell in there, it's going to show up as an interactive control for the user. And that's a website. You can take that website and put it in a server, and people can use it and can fine-tune whatever values and can tweak it, and they can do whatever they want. If we go to the end, where the actual control is, now we can see that the control is still available. And then everything else is just text with only the outputs. And this is the previous example of interact. And the cool thing that this is a website that you can publish. That's it. So the last step of the workshop, it's basically to run an actual reproducible notebook that it's out there. I'm going to show you real quick. It's by researcher Mary Chester Cadwell. She was working on text mining, English children's literature between the late 18th century and the beginning of the 20th century, looking for mentions of insects in children's literature. That's her work, that's her paper. And she published a repository in GitHub with all the notebooks and all the data. So here in corpora, claim by decade, you have all the corpora she was using. If you go to the notebooks, here you have all the notebooks, so you can fairly easily reproduce exactly the same figures that she was using in her article. It's not exactly like that, because I took this example and realized that it's not running smoothly. So I took her notebook and put it together just as one single notebook with all the 3 little pieces, downloading all the corpora from her repo, honoring the license and the citation. I'm fixing a couple of bugs in the code that made reproducible really hard. And now this notebook is reproducible. So whenever you run it, it's going to give you exactly the same. It should give you exactly the same result. It included an introduction, very basic introduction of natural language processing. We're going to skip that and go ahead and click on cell, run all. And now you can see how everything is being queued. Now we have the star everywhere. So we go to the beginning. This is just showing how to operate with variables. Sorry, you had a question? With variables that are strings, how to operate with list of strings, how you can get strings to be lowercase, uppercase, how can you check that a string is only containing alphanumeric characters, or only letters, or only numbers, or neither. How can you create slices of a list? How can you make and filter out elements of a list using Python comprehensions? And in this part of the code is where the downloading of the corpora starts. So I'm downloading and storing the corpora locally in this notebook in a folder that I created only for the purposes of this specific notebook. I'm downloading extra information, which are the name of the bugs the researcher was looking for, and also the stamped version, which is basically, in a way, is kind of the root of the word. For example, if you have a word in plural, you want the root of a word in plural and a word in singular should be the same. So that's kind of the idea of stemming. You get a root of the word that is common across many variations of the semantic family of a word. So you get the stems, You can also get the lemmas of a word. For this, I was using natural language processing as she was. So I take out all the English stop words, which are words that have not a lot of syntactical meaning. So you can get rid of them. Things like the, a, to, stuff like that. You get rid of them. You tokenize the corpus, which basically means you split the corpus in words. You have to be careful because commas are usually attached to the word, so you have to do some processing before you can have a really clean tokenized version of the words. She did all of that, then normalize to lowercase all the text, remove the punctuation, exactly as I said, remove everything that was not a word, for example, empty spaces or numbers. All of that went out. And when she had everything clean, she started to look for the words of the bugs in the literature. And for every decade, she got a frequency dictionary of how many times each bug appeared in the decade, and then plotted that information. That was all the purpose of this reproducible example of research. So if we go down, here's an example of a relative dictionary of the apparition for one of the decades. And then this script here, which he also provided, and I downloaded and put it in the repo, now is applying exactly the same process of above, all the cells in series to all the different files in the corpus. So after that is done, it's just a matter of plotting the data. I get the CSV that is generated from that run of the analysis, put that into a data frame, and then finally just do a plot with the data. And that is exactly what you got in her analysis. Now we have a reproducible notebook showing how to print always the same version of the image. Questions? I went a little fast in this last part, I know, but it was not supposed to be an introduction to natural language processing. It was just supposed to me to serve as an example of how to properly organize a research notebook so you can execute it no matter where, no matter when, and then you get exactly the same result always. That's it for me. So if you have any questions, I'll be happy to take them. Thank you. No questions means you got it all, right?
We need to practice now.
No, but we will love to digest. Thanks a lot, Javier. It was super exciting, super interesting, but I think like the majority of us have to go through once again.
Thank you so much.
Spend a sufficient amount of time. It was good.
I really hope at least you get like a little bit of excitement about, oh, that tool looks kind of cool, I'm gonna try to use it. And if you feel the thing, just try to reproduce this notebook. It's all there, it's all in GitHub. You can just download it and play with it. And if you have any question, feel free to shoot me an email.
Another question. So, do you know any of the collections or registries or whatever where we can find other use cases in humanities context for the use of not-EU technology?
Yep. Yes, I do. It's a list put together by our friend Queen Dombrowski, GitHub, multilingual DH. Good thing we have Google. And she's curating a list of resources specifically for natural language processing for all languages that are not English. And a lot of them are just Jupyter notebooks showing you introductions to topics, covering advanced topics in one specific tool, or some of them even trying to be reproducible open research notebooks. For example, here is something for Arabic, Armenian, Chinese, Dutch, German. There might be something for Spanish too. This is a tutorial. Polyglot library. It's all mixed. It's not only Jupyter notebooks, although some of them are. In this case, it's just a Markdown file explaining how to do things. But in other cases are actually notebooks. I don't know. Jupyter notebook tutorials. It's a good resource to have in hand when you are not exactly sure what kind of tool you need. So if you're dealing with natural language processing, come here first, check if your language is covered, and if it is, good for you. If it's not, then you're in trouble.